the first speaker will be Professor Arumugam MANTHIRAM. So let me briefly introduce Professor Arumugam MANTHIRAM. He is the Cochrane Family Regents Chair in Engineering and Director of the Texas Material Institute at the University of Texas at Austin. And he is a Fellow of Material Research Society, Electrochemical Society, American Ceramic Society, Royal Society of Chemistry, American Association for the Advancement of Science, and the World Academy of Materials and Manufacturing Engineering. And he is an elected member of the World Academy of Ceramics. He received the university-wide Outstanding Graduate Teaching Award and Battery Division Research Award and Distinguished Alumni Award and numerous awards. Okay, so he in 2019 he delivered the Chemistry Nobel Prize lecture on behalf of Professor June Goodenough. So now let's welcome Professor Arumugam MANTHIRAM.
Thank you. Good morning. Can you hear me?
Yes.
Thank you very much for your introduction. My talk is focused on battery chemistries for a sustainable future. So when we consider battery technologies, at least 6 main parameters we have to consider, which we are all familiar. So among them, cost is the most important one. So what I mean by that is, as we move forward, cost, sustainability, and supply chain issues will be the single dominant factor. So this, for example, compares the cost of the transition metals, which we use in the cathode of lithium-ion batteries. Obviously, cobalt is the most expensive, nickel is less expensive, but not very far from cobalt. Then, of course, copper, manganese, aluminum, and aluminum is anyway not a transition metal, and iron here. So ideally, one would like to have cells with iron or manganese to bring down the cost. But again, you have to mine them as well. So the goal in my research group is to work towards slowly eliminating the most expensive materials. For example, cobalt-free lithium-ion, eliminate cobalt. Then if you eliminate, but that means high nickel cells. So that is one of the topics I will be talking about. And next, we could think of eliminating any mined transition metal. If it is, that will be lithium-sulfur batteries. So I'll touch upon that as well. Then finally, if we try to eliminate any mined metal, then one can think of sodium-sulfur batteries or sodium organic batteries. Sodium is plenty in the ocean. Sulfur is a byproduct in the petrochemical industry. So that's the kind of things I mean by sustainability. Some are near term, some are mid term, some are long term. So these are the 3 topics I will be covering, the ones listed here. So first, elimination of cobalt. So before I go into the details, I would like to mention 3 things. One is we make our own material. We can make any particle size of secondary particles, but normally we use 12 micron secondary particle size. We can scale up the hydroxide precursor in my lab, 10 kilogram per batch. And then we also make pouch cells. Then we have graphite. Lithium also we do to some extent. And then third, after cycling for large number of cycles, we have the capability to open the cells after thousands of cycles to examine by different techniques, XPS, top spins, SCM, TEM. And on the process, we also can use solid state NMR or liquid NMR. And if we need synchrotron, then we go to national labs in the US. So eliminating cobalt, we were successful actually to eliminate cobalt. I'm comparing 5 materials here. All of them have, 4 of them have 90% nickel and 1 of them has 60% nickel for a comparison. This is the material NMA, means 90% nickel, 5% manganese, 5% aluminum. The composition is written on the title. And that performance is here. This is pool cell, pouch cell, 1000 cycles. So as we see here, the material that does not have any cobalt gives performance similar to or comparable to other cobalt-containing materials. So cobalt may not be necessary as we move forward. General belief is cobalt may affect the rate capability drastically, but we don't see that. And safety-wise, again, the NMA without any cobalt is right here, which is better than or comparable to other cobalt-containing materials. This was done 2 years back. Now, in the previous one, you saw some dopants as well. So one of the things you want to understand is which dopant does what. So I'm going to compare 4 materials here. LiNiO2 itself, no doping. And then 5% doping of cobalt, manganese, or aluminum, Nc, Nm, Na. One thing to remember is as we go from LiNiO2 to doped material, there is a decrease in the capacity if we limit the cutoff voltage to certain voltage, for example, here 4.4. So that we have to keep that in mind. With that cutoff voltage, if you look at the cyclability, obviously the aluminum and manganese doped material cycle will be better than the undoped LNO or Nc. So I give it in a different way. The bar graphs are capacity, the red dots are cyclability. Obviously, Nm and Na cycle well, but the issue is with the same cutoff voltage, could the improved cycle life with doping be due to the lower capacity? Because we are not comparing apple to apple, capacity is decreasing, the cyclability is going up. So the best way to compare is to have all of them subject to the same cutoff charge energy density, that is 750 watt-hour per kilogram, that is on the cathode level. If you do that, then the trend is exactly the opposite of what you saw in the previous plot, meaning LNO and Nc in fact shows better cyclability than the manganese and aluminum dope. And why it is, we have looked at the impedance as we see here. Manganese doping leads to larger impedance, and that also leads to increase in voltage and polarization. That's why the cyclability is falling off. So why manganese causes more impedance? So if you see cross-sectional SEM here, now you can see a little bit cracks forming here, and Na maybe a little bit much less, but a little bit. These two do not show any cracks. So the impedance increases obviously due to the crack formation. So the next question is, why manganese doping leads to crack formation? So we have tracked the H2, H3 phase transformation by having under 3 circumstances. This is 003 peak, X-ray diffraction peak. So first 4.4 cutoff voltage or 80% state of charge in all of them. If you do that, we clearly see the H3 phase forming. In this case, for example, small amount. In these two comparisons, we have H3 phase formed to a greater extent in the case of manganese doping, and that's why it leads to cracks and then more impedance growth. This is the cutoff energy density of 750 watt-hour per kilogram. Again, in that case, none of them show the H3 phase excepting manganese. So the first point we need to understand here is that the H2, H3 phase transformation does not occur at the same lithium content or at the same state of charge. It is different, particularly in the case of manganese doping. It occurs at a slightly lower state of charge. That's why we have this issue. So manganese we see is as a problem. Largely it is fine, but on a comparative scale, we see some issues with the manganese, particularly H2, H3 occurring at a lower state of charge and then leading to H3 phase formation. So now I'm presenting here a composition without any cobalt, without any manganese, and that is NaTm with 5% aluminum, 1% titanium, and 1% magnesium. That is compared with 2 other materials. The compositions are given here, and all of them have around 90% nickel and the nice X-ray diffraction patterns. Only in the case of NaTm, we see the titanium a little bit on the surface. It is also in the bulk, but a little bit more enrichment on the surface as indicated by time of flight secondary and mass spectrometry. and EDS analysis. And they all have similar particle size as you see here. So now a few things again here. When we go from nickel cobalt to NaTm, there is a decrease in the voltage, as I said earlier. So there is a decrease in the capacity, as I said earlier, and also a small changes in the voltage. The peaks, as you see here, 25 milliamp more, and when you go to NaTm, 51 milliamp, and we don't see any much changes in the rate capability. This is a cyclability with the lithium material anode. You see, obviously NaTm cycles better, but sometimes the cyclability could be due to lithium problem or cathode problem. To avoid that, we have used graphite as an anode, 800 cycles. Obviously, clearly, the NaTm shows 82% retention after 800 cycles. That's remarkable compared to the other two materials. So the question is, why these kind of dopings help to have better cycle life? So we have done a lot of characterization of the cycled cathodes after 800 cycles from this cell. So first, this is time of flight secondary and mass spectrometry. The green means the layered oxide. The red color on the surface is the CEI, the interface layer formation. I'm also showing the data in the form of a bar graph. So NC shows the highest amount of electrolyte decomposition. The red is NMC, less decomposition. NaTm has the lowest electrolyte decomposition among the three materials. That is also consistent with the thicker CEI formation here with the NC, medium CEI thickness, the least CEI thickness. So it's all consistent. If you look at the crack, NC has more crack, NMC has less, and NaTm has obviously the least amount of crack. More importantly, after 800 cycles, if you look at the X-ray diffraction pattern, particularly this 003 peak, the faint curve means initial, the thick curve means for each material after 800 cycles. So if you see here NC, there is a big difference in the location of the 003 peak. That means the active lithium there is a loss of more active lithium in this case, medium loss, here the least loss. So clearly, lot of lithium, active lithium is consumed in the CEI formation, and that's why the cyclability is fading. This is safety or thermal stability. The same kind of trend, NC, the lower temperature, more heat release, NaTm has the highest temperature and the least amount of heat release. And that is, you can understand that obviously, when you have these ions, they form very stronger bonds, a little bit more stronger compared to cobalt oxygen or nickel oxygen. They are more, the metal oxygen bond can very easily break with cobalt oxygen and nickel oxygen. Magnesium, when you have small amount, it goes to the lithium layer. So it can act as a pillar. So it can delay the layer to rock salt phase transformation. Titanium is on the surface, so that can help to have a better stable surface against the liquid electrolyte. So far I talked about cathode surface stabilization and bulk stabilization. Now I'm going to move on to electrolytes. So I compare here with the same, the LiNiO2, that is the worst cathode we can think of. The reason we do LiNiO2 is there is no doping, there is no complication, just high nickel, 100% nickel. So we can clearly understand what is going on without having any other complication. And it's also the worst cathode in terms of stability. Therefore, we can have a better understanding of the differences. So 3 electrolytes, LP57, the conventional electrolyte, LSC, localized high concentration electrolyte. Compositions are given here. That was developed by PNNL, Pacific Northwest National Lab, as part of the Battery 500 consortium. I am part of that consortium as Selenium, who is sitting here. The third electrolyte is, we call it as localized saturated electrolyte. 2 advantages here. It uses the carbonate, so they have higher voltage stability. Second, no longer LiFSI is necessary. We use LiPF6 here, and TTE is the diluent. So the compositions are given here. Let's look at the performance, the capacity retention. Day and night difference. The LP falls off pretty fast. The LSC shows much better than even LHCE. This is the linear sweep voltammetry. You can see compared to LP57 or LSC, LHCE, LSC shows a little bit better high voltage stability, and that has consequences. This is another electrolyte. This is completely baseline, and another carbonate electrolyte. In the carbonate 20 F1P, it has 28% APC and 1% LiPo2F2 compared to the other electrolytes. So we are comparing here. If you do that, again, there is a big difference in the cyclability. The voltage is, the capacity is falling off here, but the stabilized electrolyte has much better cyclability in both of these two plots. So why it is happening? So this is the SEM images of the secondary particles, LP57. After 200 cycles, maybe a little bit crack, but we don't see too much. The other electrolyte has already 200 cycles, you see some crack, secondary particle crack. If you go to 400 cycles, lot of secondary particle crack, but it is surprising. This has crack, but if you look at the cyclability, it is exactly the opposite. So if you look at the TM, in the baseline electrolyte, you can see small micro cracks in the primary particles. In the other electrolyte, 20 F1P with the FEC, we don't seem to see much primary particle crack at all. So it turns out in LP57 conventional electrolyte, more secondary particle contact, there is aggressive surface reaction. That's why this happens. Here, less surface reaction, and therefore we don't have much primary particle contact. And then why the secondary particle is cracking? You can look at the X-ray peaks again. In the case of LP57, initially you see H2H3 phase transformation, but the capacity is falling off like crazy. So when you keep on cycling, after maybe 100 cycles or 50 cycles, you do not go through the H2H3 phase transformation. You don't see any H3 phases forming. So that's why we don't see much secondary particle cracking. In the case of the other electrolyte, which cycles well, you have H2H3 phase transformation initially, as well as 200 and 400 cycle. It is maintained. That's why it is cracking more secondary particle cracking, because you are going through a lot of this phase transformation in this case, but it does not cause any primary particle cracking. So overall, surface reactivity is the dominant issue that has consequences for crack rather than crack itself. Or in other words, if you have good electrolyte, you can try to overcome the problems with the crack. That's what I'm trying to say. So why the other material cycles well? Another reason is I've listed 4 materials here. This is the original. Sorry, there is a typo here. Li 0.15. This is not 85.15. That's a layer structure. During on the surface reaction, this material forms Li2O4 in the case of good electrolyte. Both 2 good electrolytes I showed, LSC as well as that FEC with LiPo2F2. Both of them form only mostly LiNiO2 on the surface. In contrast, if you have the conventional electrolyte, we form Ni3O4 spinel and NiO. Or in other words, in the case of good electrolytes, the cathode surface is not reduced very much. It stays around 3.5 LiNi2O4. That's a good 3-dimensional spinel structure, excellent electronic conductivity, excellent lithium-ion conductivity. So it does not cause much problem. Ni3O4, you have nickel ions in the tetrahedral side, really bad, poor lithium-ion conductor, and it is reasonably poor electronic conductor as well. Nickel oxide, I do not have to explain, both of them are bad. So this is why surface reactivity, which is formed on the surface, good electrolyte versus bad electrolyte, stable electrolyte versus unstable electrolyte makes a big difference. Now elimination of, those are all so far with layered oxides. Now I'm moving to elimination of mined metals except lithium. So that means lithium-sulfur. So lithium-sulfur has a lot of advantages: 2 electron transfer, huge capacity, abundance, but there are few problems. Poor electronic and ionic conductivity, that leads to low utilization and low capacity, practical capacity. Polysulfide shuttle, again poor cycle life, and it also leads to self-discharge. More importantly, if you use sulfur, we have to use lithium metal anode, and that leads to poor cycle life and safety concerns. So largely, many, at least in the past, lot of work has been done with very low sulfur rating, very high electrolyte amount, and then high amount of lithium as well. And if you do these kind of things, the practical energy density will be pathetically low, maybe less than 50 watt-hour per kilogram. So what we need to do is to have these parameters under control, and PATI 500 focuses very heavily on having these parameters under control, for example. So ideally, can we have carbon content less than 5%, sulfur loading at least more than 5 milligram per centimeter squared, electrolyte to sulfur ratio less than 5 microliter per milligram, and then lithium amount again less, or ideally no free lithium on the anode itself. So how do we achieve this? Reduce the excess lithium by stabilizing the lithium deposition with various additives. I will touch upon that. Reduce the porous carbon by replacing it with electrocatalytic cathode hose. For sulfur redox reaction to happen well, we need catalysts. So if we use dense catalysts, that can reduce the amount of conductive dense catalysts, that can reduce the amount of porous carbon. And obviously, if you do the first two things, that can help to reduce the electrolyte amount. And more importantly, the performance has to be demonstrated with pouch cell with reasonable loading rather than with coin cell, because coin cell's performance can be very deceptive in the case of lithium sulfur batteries. So with that, because we won't have too much time, eliminate a lot of slides. So first, if you look at sulfur, selenium, and tellurium, they're all in the same group in the periodic table. So here we take Li2S, and we are doing, at least as you see here, anode-free cell. That means we take Li2S on the cathode side. At the anode side, we can make a cell with the lithium metal, one option. The other configuration is we have Li2S with a nickel current collector on the cathode, and the anode, there is no free lithium at all, so it is called anode-free full cell. So this is similar to lithium ion cell, excepting you will have graphite here. The cells are assembled in the discharge state. So we are going to compare these two configurations. First with the Li2S cathode alone, then the second 10% sulfur addition to that, 10% selenium addition to that, 10% tellurium addition to that. So if you look at here, selenium addition obviously helps to increase the capacity. This is a cell where we have excess lithium on the anode. Because the selenium addition helps to have better redox with helps to increase the conductivity, and it also helps the redox reaction, so capacity is increased. If you go to the anode-free cell, the same four things, if you look, only tellurium addition maintains good cycle life. The others have poor cycle life, because here the lithium is limited. Only the lithium is coming only from Li2S. So this is the best way of understanding what is doing what, because we do not have a lot of lithium floating around. Here it is not limited by lithium because we have too much lithium. So selenium is trying to show up its advantage. Here, lithium is the limiting factor, so selenium advantage is not seen. So tellurium is doing something that makes the lithium cycle better than selenium or without having any tellurium. So I've done a lot of XPS as well as toxins. So I will given the data here. So what happens here is, if we have only sulfur and selenium with lithium nitrate added to the cell, the sulfide or polyselenosulfides moving from the cathode to the anode, they tend to get oxidized to oxidized species, sulfate containing species. You see here, more oxidized species here, more oxidized species here, less sulfide or selenide kind of species in the XPS. The same thing can also be seen in the case of toxins. You have more oxidized blue here, less reduced species. So there is a big oxidation going on to form oxidized species. If you add tellurium, that kind of oxidized species is reduced. You have more sulfide and telluride kind of species. That is shown both by XPS as well as by time applied secondary and mass spectrometry. Exactly the opposite. Here blue is more, here red is more. So you can clearly see. If you look at the lithium morphology after cycling, you have rough morphology. With tellurium addition, you have better morphology. So what happens when we add tellurium or selenium is they form polyselenosulfides, meaning selenium substitutes into the polysulfide molecules. In the case of tellurium, it does the same thing. It forms polytellurosulfide, and that migrates from the cathode to the anode side. At the anode side, it forms Li2TeS3, and that acts as a good artificial in situ created SA layer, so that helps for the better cyclability of the cell in which we have added tellurium. So this is the LIS pouch cell with having lithium metal on the anode side. This is anode-free cell with the Li2S and pouch cell. You can see in both cases the tellurium addition. This is anode-free, amazing. It gives much better cyclability, but the capacity is lower. This is per gram of Li2S, not sulfur. And also, we have not added any catalyst here. So, add catalyst, electrocatalyst, then it helps the redox reaction, the capacity will still go up. So, I just want to point out, this is per gram of Li2S, that's why the value may look, value looks lower. But obviously, the most important point is the cycle life. Tellurium addition changes it, and that is because without any tellurium, you have more oxidized species. When we add tellurium, because of the formation of the Li2TeS3, we have better cycle life. We have also done modeling with tellurium, selenium, and without any of those additives. Clearly, the Li2TeS3 formation provides better lithium diffusion or lithium diffusion pathways with lower energy barrier. That's why the lithium is able to diffuse through that much easier, keeping better cyclability. Finally, as I said, I didn't talk too much about catalyst, so I have one slide. We have to make dense lithium-sulfur cells with the electrocatalyst. So here I show one-step synthesis. I use cobalt here, but it need not be with cobalt. The same reaction can be done with manganese or nickel or iron as well. So we take, for example, manganese sulfate or iron sulfate or lithium sulfate, add carbon, carbothermic reduction. This can give, depending upon the quantities of each of those, you can have a metal sulfide, sulfur, cobalt, or other metals, and carbon dioxide is going out. So these can give fairly dense cathodes. So I compare here the cyclability of three materials here with the manganese in the reaction. Not cyclability is not that great. Nickel is better. Obviously, cobalt is better, but we cannot live with cobalt. We need to find other ways. But in any case, the cyclability is still better. And then I'm comparing here three cases, only Li2S and carbon, no catalyst. That's the cyclability. You see here, if you add this kind of reaction, make it the red curve. And then if you add tellurium into that, then that stabilizes the lithium. So the black curve is the best, where we have catalyst to have better redox. At the same time, we also have tellurium to stabilize the lithium plating and stripping to get the best cyclability. Now my final topic, elimination of mined metals altogether. So that is obviously sodium-sulfur. This is actually a dream technology for me. So I compare here three cases, NaTFSI with PC, FEC electrolyte, and NaClO4 plus NaNO3 with TgDMe, and then a localized high concentration electrolyte, and that composition is given here. The localized high concentration electrolyte we have used is NaTFSI with DMe and TTE. Few things here. In the first two cases, we see more gassing, and we also see more dendrite formation compared to the localized high concentration electrolyte, and more importantly, more over voltage. In the case of the use of LHCe, we get much better symmetric cell cyclability compared to the other two cases. So again, I talked a lot about electrolyte in the case of high nickel layered oxide cathodes. Clearly, electrolyte plays a much major role in all these systems compared to the cathode or anode itself. So just the electrolyte change, everything else is same here. So now we have also done a lot of characterization to understand what is really happening. So this is in situ XRD in the case of localized high concentration electrolyte with the sulfur, sodium-sulfur system. Obviously, we start with alpha sulfur 8. This is first discharge. During that, we get Na2S5. That is the polysulfide. It is forming. Then if you go here, we get the formation of beta S8, as one would expect. And then you can see the intensity here, lot of Na2S5, the red color. When you do the second discharge, that's diminished. When you go third or fourth, we don't see any Na2S5. We have also done a lot of characterization, both with NMR as well as with XPS. So it turns out the NaFSI salt we use in the localized high concentration electrolyte, that reacts with the polysulfide formed initially during the first cycle to form a cathode SEI containing sulfur fluorine species as well as sodium fluoride. That's what these characterizations show, NMR as well as XPS. So this is what is really happening when we use this electrolyte, that is electrolyte salt, the polysulfide interaction. So that leads to the formation of these. So once it is formed, that seems to change the reaction chemistry pathway from a conventional dissolution precipitation reaction into a quasi solid state kind of reaction, because we don't see the polysulfide formed after 1 or 2 cycles. So that it gives much better cycle life with high capacity in the sodium sulfur cells. So overall, my conclusion, near term elimination of cobalt. I think cobalt is not necessary. 622 is very much commercial. 811 commercial and not commercial. Some companies are successful to make it very well. Some companies are not, but pretty soon that will become a standard. But I would like to mention here, because I showed data on LiNiO2, all the companies, major companies are now focusing on 95% nickel. I know that some companies are working with, we are working with. So I know the trend is like that. 8112, higher and higher nickel. I don't know where it will stop, or at one day, maybe LiNiO2 maybe become useful. I also have a lot of gas generation data, which I did not put it over here because of want of time. So that is the near term. It will happen pretty soon. It is already maybe happening. Mid-term to long-term, elimination of nickel, and that is lithium-sulfur. Long way to go, a little bit. Right now, there are companies who are making cells. They are limited in cycle life, maybe 150 cycles or 200 cycles with fairly reasonable energy density, 300 watt-hour per kilogram or 350, around that. So it is just getting there. Only 10 years, very much work has been done. And then elimination of lithium, sodium ion cells. Lot of things are happening again. Possible long term, the elimination of mined metals, maybe sodium sulfur cells. It may take much longer than lithium sulfur because not too much work is done. You already saw at least in one of them, the electrolyte make a big difference compared to the conventional electrolyte versus the localized high concentration electrolyte with sodium sulfur cells. So I think there are a lot of activities happening all over the world. I think there are possibilities. Some systems we think impossible may become potentially possible. So finally, I would like to thank my group. This is my current group, as well as the funding agencies, particularly the Department of Energy, ERE. A lot of work I presented today is related to battery 500 and another ERE VTO on the high nickel. Thank you very much. I'll be happy to answer questions.
Okay, thank you. Thank Professor MANTHIRAM for your nice talk. So now we have time for a few questions. So any questions?
Hello.
Yes.
I have a question. Thank you for your wonderful presentation. In your presentation of 12 pages,
Well, I'm not really.
12.
Slide 12.
Okay. Next one.
Yeah. You mentioned that the H2 to H3 phase transition at a lower state of charge in nickel manganese. I'd like to know why, since it is reported in some paper, the manganese is inactive for the cathode. So it seems that will demonstrate a higher platform of the phase transition.
Okay, first, you can look at here, aluminum is inactive as well, manganese is inactive, cobalt voltage generally higher, so I would expect nickel oxidized more or less, nickel band, 3D band is a little bit up compared to cobalt. I would say in nickel cobalt, nickel is largely oxidized, not cobalt, so I don't think the inactivity of the metals are causing these differences, because in all these cases, I think nickel is the one undergoing redox. And then when we dope all these materials, the ionicity, covalency of these bonds may change. There are a lot of things may go on, which I don't know. You are asking me why it is happening at a lower state of charge. I do not have the answer. The only thing I can say is these will make a lot of changes in the bonding, particularly when you have nickel and cobalt, they will have the 3D band a little bit broader. When you go to manganese or aluminum doping, they may introduce little bit localization, because they are not transition metals, that they have edge-shade octahedra, the electron flow will be a little bit, hopping will be a little bit disturbed, because manganese and aluminum will act as speed breakers. So that can cause the so-called physics community knows that, the so-called Anderson localization. It may introduce impurity levels, narrowing of the band, so they may have consequences. So I do not have any direct answer for you, but I can very well understand the changes in bonding can cause these kind of problems. There is no reason they have to occur exactly at the same place, because there is a lot of chemistry will be changing when you dope.
Okay, thank you for your reply.
Yeah. Thank you for the question. Huang, you are muted. Haita, you are muted.
Sorry, there is one question in the chat room. How can you determine the chemical state of nickel vacancies in the lithium nickel oxide?
Nickel vacancies where? Nickel.
The chemical state of nickel vacancy.
No, maybe nickel ion, not vacancy, right? Vacancies won't have any chemical state. So nickel valence.
Yeah.
You can do only. I mean, once you know in the beginning how much lithium you have extracted, you know what the oxidation state will be. Otherwise, if you want to use some equipment, you can obviously use XPS, but that will not be accurate. Any technique we use, it will not be very accurate. There will be error, some error. But once you know the capacity, at least in the beginning, we will know based on the lithium content how much, what is the nickel oxidation state. Maybe This is the one referring to, how do I know? Again, this is a typo. This is lithium 0.15. In that case, nickel oxygen state is 3.85. That is calculated based on the lithium 1 plus and nickel valence we calculate same here, same here. Maybe that's why that person is asking that question. Again, I'm sorry, this is 1 pi. Valence state 3.85.
Okay, thank you, Professor MANTHIRAM, once again. So now